There was a question on the way we apply closure to our full domain omega and to the union of our subdomains. So let me revisit that little bit and clarify something. So let's recall. Let's recall the finite element partition. Okay, so we know that we have these subdomains omega sub e, and each subdomain omega sub e is the open interval xe to xe plus 1. Okay, and here's the picture. We have here, we have the point 0, that is the point L, right? X equals 0 and x equals L. We denoted this point as x1, and we have other nodes here. Okay, that is x2 and so on for a general subdomain which is an element omega e. We have xe and we have xe plus 1. Okay, and as the manner in which I've written omega e, it is clear that it's an open interval. Now recall as well that omega, the domain of interest, is this open interval. Okay, so whereas omega does contain the nodal points except for x1 and x, I believe I call that xn, but we know, yeah, that's xn. Okay, while omega contains all the nodal points except the first and the last. Okay, each omega e does not contain its own nodal points. All right, so omega contains the points x2, x3, so on up to x n minus 1, and I note that we since we're using NEL for number of elements, we also have the following relation, right? We also know that the total number of nodes is equal to number of elements plus 1. Okay, let's just remember that because we may later on we will want to use maybe NEL to number everything. Okay, so this is the important point. Omega does contain these nodal points, right? But it clearly does not contain x1 and xn. Okay, so as we can see, there is, omega and the union of all the omega e's are closely related, but they're not quite the same. Okay, in particular, what we can see clearly is that omega itself is not just the union over e of the omega e's. Okay, why is this? Because each omega e does not contain its own nodal points, whereas omega does contain the interior nodes. All right, the only way we can connect them, the only way we can relate omega to a union of the omega e's is to make sure that we pick up all the nodal points. Okay, the nodal points, by the way, are otherwise referred to as the limit points of the corresponding open sets. Okay, so the way we can do this, however, is to say, now if we apply closure to omega, what we make sure is that it does indeed pick up the nodes x1 and xn. Okay, and in order to make sure that it is equal to some other closure, what we do is to go back to our union of the element subdomains. Since each of those subdomains is an open set and these are disjoint open sets, we know that this union on the right hand side of the velocity equation, this equation by the way is not yet complete. We know that what I have on the right hand side is still missing all the nodal points. Now when I apply a closure there, I make sure that I pick up all the nodal points including x1 and xn. Okay, so in this form, so this contains all nodal points x1 all the way up to xn. Okay, it's really a technical requirement because it turns out that when you do the integrations, the fact that you may be missing just one point does not really make a difference to the type of integrals we will consider in the problems of interest. It's a technical point, but then it's an important one to recognize just in case it leads to confusion later on. Okay.